Hello everyone, welcome to my YouTube channel. Today I am bringing you the senior scientist of NASA. He was working for NASA for decades as a principal engineer and now the senior scientist, research scientist. So this was kind of an interview I was waiting for. I got the appointment I waited from the beginning of this year, and since I'm also into aerospace aviation domain, hopefully I wanted to have this interview as soon as I could, but with the busy time schedules, Goutam gave me this time slot, and actually it's a great pleasure to have him today to share his experience, insights and advices to every one of you. Nice to meet you via online platform, and thank you for giving me some time. I know that you might be a super busy person.
No problem. That's my pleasure.
Okay. So Gautam. So let's start. So I'll give a brief introduction. So I'm trying to reach global lead. Some of the people with the leads I had to work with, since I'm also in the IT industry, and these days I'm working Rolls-Royce safety management solutions. Before that also I was in airline aviation domain. So NASA is everyone's dream place, workplace, and dream place to join in is. So that's why I thought of reaching you. So to start off today's conversation, I noticed that you have been working for NASA for years, being a principal engineer and then a senior research scientist. So can you give a brief introduction about your background?
Yeah, sure, absolutely. So I actually grew up in India. I did my undergraduate from India, near Kolkata, that West Bengal is the eastern part of India. And then I did my undergraduate from Bengal Engineering College under Calcutta University. That is the second oldest engineering college in India. And after that, I actually worked in a couple of years. One of the research institutes is called Tata Institute of Fundamental Research. So what they were doing at the time were building a radio telescope at the meter wavelength. So it's a very large telescope array. And I was a part of the team, a very young engineer. I was given the opportunity to develop one of the systems. So I did that, but I realized at the time that, you need more formal education. Because if you want to make a really an impact, you need to have the training that you need. So I went for higher education. I came to US as a graduate student. I did my master's from University of Virginia, that is in Charlottesville, and then I wanted to continue to do my to PhD. So I applied to Caltech, California Institute of Technology. And then I was very fortunate that I got admission here and then came. One of the interesting part is that even though I was doing my PhD in electrical engineering, but my thesis advisor was in the physics department. So I used to actually sit in the physics department, and there, one of the story I actually tell that is very inspiring, that every winter, 2 doors down from my office, it used to be Stephen Hawking used to come and sit there, and he used to spend his winter at Caltech, and I used to actually meet him, talk to him. It was kind of unreal feeling. Then from there, then I was thinking, okay, what I should do. When I was kind of finishing up, one day I got a call from NASA saying that if I was interested in joining their NASA-Jet Propulsion Laboratory, that is in Pasadena, California. And so, of course, as you said, every child's dream is to work at NASA. So I was so thrilled that I got this call. So I went out there and gave a talk and interacted with the people, and then started working there. And ever since, it has been, I joined there October 1st, 1999. It's about 25 years now. So, but every day it still feels new to me, because there is so much of excitement going on, that you are surrounded by the best of the best around the globe. So that is, I got involved in doing some of the very nice, exciting projects as well, some astrophysics related, some planetary science, as well as Earth observations, because I build instrument. I'm an instrument designer, as well as connect the dots between the science and the instrument. So that's my role. So in that role, I won't give up anything. I really, every morning I go there, I'm excited to go back there. So that is a dream job for me. So, and on top of that, they pay me. So it's kind of, that is my story of getting from Novogram, that village that I grew up called Novogram. So that's my story from Novogram to NASA.
Thank you. Inspiring, actually. So, what actually inspired you to pursue a career in this kind of space exploration and engineering? Since you told that you were into electrical engineering, you studied electrical engineering, and yeah. So,
Yes.
can you share some specific
Yes,
experience?
absolutely. So what from the big, as a childhood, actually, I had kind of a dream, like as you said, for many of us, I had a dream of NASA, because I used to read in the newspaper at that time about what's happening, about Apollo missions and stuff like that. And as everyone, when you look up in the sky, you see in the dark sky all those stars. That has kind of allude to that you understand what is going on, how we all came about, how the universe formed, all these big stars, all these planetary bodies that out there, how did that all form? So there's so much unknown, right? So I had that inclination in me, and that's why when I got the opportunity to do work after my undergraduate, I had joined in that TIFR I mentioned, Tata Institute of Fundamental Research, and they were doing radio astronomy. And actually, in a way, that opened my eyes, because I was interacting with very famous radio astronomers in the lower frequency band, in the meter wavelength, like Govind Swarup in India. He's considered the kind of the father of radio astronomy in India. And then there was Jayant Narlikar. He is an astrophysicist, very famous astrophysicist. So I got the opportunity to meet them. That opened my eyes. So that from there, I more or less, as I said, from the beginning, I was more inclined towards NASA. And then when I started studying and was in the physics department and started seeing all the discussion that was going around. So that inspired me more to pursue a career in this way, in this direction, because you need, to do the science that we do at NASA, you need to build the instruments. Basically, everything that we do here, it is this all anchored to the science. So always it is about what science question we are trying to answer. If you look in the sky or anything, the science is that we are trying to answer questions, right? We are trying to find the truth, that how things happen. And also there are some theories, but theories are theories. You'll have to have a confirmation, observation, measurements to confirm those, and theories change based on the measurements and the observations that is done. So you need to have this kind of skill set to understand what science question you are trying to answer, and then what kind of measurement that's needed to answer those science questions, and then what kind of instrument that you need to build that will do the measurement. And then you look at what are the technology gaps out there, that if I have to build this kind of instrument, what are the technologies that we need to develop. So this is very exciting path for anyone, and that's inspired me. That is the reason I actually chose this path.
Got it. So you are working, you should be involved in several different projects, groundbreaking projects at NASA at the moment. So can you share some details or the experience about the project you are working, and what kind of an impact uh, they can give us, those who are interested in space and technology?
Yes, of course. I have been involved, as I said, quite a few different projects. One of the exciting things that I'm doing right now is, that one of the biggest science question that all of us are trying to answer is, are we alone in this universe? Is there life beyond Earth? Just to be sure, I just want to make it very clear that we have not found any life anywhere else. You might have read in the internet or saw on YouTube that there are aliens, but we have not found any. We have not even found a single cell life anywhere else. So, but that is a bigger question, because that is one of the big science thing that is we want to answer. And in that respect, if you think that what is the probability that life can exist? So if you look up in the sky in our Milky Way galaxy, we have about 100 billion, order of magnitude, we have about 100 billion stars. And then in our universe, we have about 100 billion galaxies. So if you do your math, there are many number of stars, in terms of 22 number of stars, order of magnitude in our universe. And we are finding that many of those stars, actually majority of them, they have planets around them. They are called exoplanets. And not only one, multiple planets. And many of those planets we are finding that are in a habitable zone. What we mean by habitable zone, that their conditions are such that life can exist. And what are those conditions? When we're talking about life, we generally talk about our kind of life. That's what we understand. It's called the hydrocarbon based life. And for that, we need a few very basic elements. One of the things that we need is water. Of course, our kind of life needs water to sustain, and few other molecules, carbon, hydrogen, nitrogen, sulfur, oxygen. So those are the things that we really search for. And it turns out very interestingly that we still don't know how the water in our solar system and our planet Earth came, that from where the water came from. And scientists believe that the comets brought water to Earth. One particular kind of comets we call Jupiter family comets. And for that, if you want to prove that comets brought water to Earth, you'll have to do some experiments, you'll have to do some measurements. And one of the things that we want to do, the measurement, it turns out that if you look at the water, there are different kinds of water. One of the water is that what we drink every day, that is the most abundant water, that is H216O. Oxygen has different isotopes, right? And that can form water like H217O, also can be one kind of water, H218O, and HDO, like one hydrogen, one deuterium, one oxygen. And we all know about heavy water, D2O as well. So there is all these different kinds of water. If you take the ratio of abundance of different kinds of water, and also the deuterium over hydrogen, that these two ratios, we are finding that is very similar to some of the comets. And these ratios has to be same if the source is the same. However, we have not made that many measurements so far. We have done about maybe a dozen measurements, not statistically significant. So what we thought that we can do is that, can we build an instrument that can address this question? That we can make something that is small enough, that is light enough. So it's like a shoebox-sized satellite that we can build multiple of them. They can go to multiple comets and do the measurement of these. These are very high resolution measurement, high sensitivity measurements one has to do. And if you can do that and then answer this question for once and all, and that will be huge, kind of a contribution towards science. So right now we actually just completed building one of such instruments. Trying to we did some experiments using a balloon as well. So that is very exciting because we are now waiting to get a ride to go some of these comets and do these measurements. That is one area that we're working on. Another area that I'm really involved right now working on is climate change, climate science, because that is one of the most important area that we really need to focus on, and particularly for young people like you, because your future depends on what we do now, what kind of decisions we make, what kind of science that we do. So one of the things that I'm working on is an instrument called MLS, is a microwave limb sounding instrument. How it works is that if you look at the stratosphere, it turns out that many of the pollutants that the human man-made pollutants, transportation happens through the stratosphere. And then we need to know, how these things are, like, all these different these molecules, different they are coming to the stratosphere. Even the water vapor is one of the greenhouse gases that we can study from there. So I'm part of the team. We are building the next generation of this kind of instrument that will study this transportation of the pollutants that is in the Earth observation side. I'm also involved in other astrophysics missions, that is building instruments to know how new stars are formed. One of the things that if you try to understand how our universe came about, that how we all came about, how planets are formed, you'll have to really look at understand the process, how new stars are formed, how galaxies are formed. And one of the things that is very interesting is that if you look at, these are hot gases, hot plasma, hot kind of gases are the dust and gas. From there they coalesce and then they form stars. Then from there, galaxies are formed, and then from there planets are formed. One of the things that for that we wanted to look at is I'm just giving a little bit more detail than is necessary, but it's about a called C+ line that is at 1.9 terahertz. Atomic carbon has a rotational transitional frequency at very high frequency at 1.9 terahertz. And if you map the distribution of that C+, that actually acts as a coolant for those gas, which means that if you can map that out, that it can tell you what is the chances that this gas and dust will coalesce and form a star. So I'm building instrument to understand that. And also for planet, I am involved in some Mars instrumentation. We are developing some radar to understand what is the water vapor on Mars, and also how you measure the wind on Mars, because it is very difficult right now. It's not much measurement has been done on the winds on Mars, because that also tells us how the different atmospheric molecules they transport in the atmosphere of Mars. So I'm involved in all the different kind of projects.
Okay, so one question came to my mind, like, so when you're building these equipments, when you're exploring these different planets, whether can be like the people can go and survive. So if that instruments can build so that H2O, the different kinds of, like, there may be some H2O, like not the H2O or 16, 17, 18. So if that equipment can make the components which will be helpful to survive the lives.
When we are doing all these measurements, we are actually not, in the sense that we are not transporting a human being. We are sitting from the space. We are trying to observe which is far off places, and trying to understand what is going on there. Right? These are all remote sensing based instruments. And even if you, I mean, I think that what you are also trying to ask that if we, when you build such instruments, suppose we are going to those places, let's say go to those planets, we'll have to, how do we take care that we don't take life from here and then detect it there, right? So yeah, we are very careful about those things, planetary protection. And then so in basically what happens is you build an instrument, you go as close to the comet as possible. For this water, we go to the very close to the comets and do a measurement from little bit far. We do not need to land on the comet. We do not need to collect this water sample from there, water vapor. We can actually observe them a little bit far and do all these measurements. So that's the beauty of this. And then get the data and think, okay, they know what is the abundance of all those, what is the ratio of different. So that is what, and there is a lot of not just building the instrument, there's a lot more things go behind that to make sure that we understand what we are measuring.
Okay, so we all know that technology plays a pivotal role in space explorations, like with these upcoming trends and like emerging technologies. We are having AI, machine learning, data science. All these things are shaping up the missions at NASA as well. So how do you see and how does NASA get the use of these emerging technologies?
Yes, that's a very good question. Because as you see, there is two sides to this AI ML, the discussion that's going on right now everywhere. So this is amazing technology, right? AI and machine learning. But there is a dark side to that, we all know that what it can do, what can harm that it can do. But our position is that if there is some new technology that is there, you should use it to make, so that we can design things better. Right now we are actually using AI and ML technologies to do our designs better, right? You can do, it used to happen is before, I'll give an example. Suppose you are trying to build a component. We understand the theory and all, and then from there, we start somewhere, do a basic design, and then we try to use a lot of simulators are there. We use those simulators like electromagnetic simulators, circuit simulators, and all other kinds of simulators, physics-based simulators. We use those to optimize our design and then come up with a final component. However, if you look at them, they look very traditional in the sense they follow certain physics-based rules, right? They look, we already know from the beginning that how they're going to look like. However, if you go back to the artificial intelligence domain, you can actually, it can be completely disruptive in the sense that you start with this is the output I want. This is my input. And these are the boundary conditions. That because if you're making something, it has to have some boundary conditions. You cannot have something that is impractical to realize, right? So if you put those boundary conditions and let the artificial intelligence, come up with the solution, you might find that that solution is somewhat better, but one can never even imagine that it is kind of a circuit, because it is looks so random, so chaotic, but there is a method to that chaos. So it can actually do wonders to develop new components and stuff like that. So we are already doing, for like our last Mars mission, we had that Perseverance rover. When it was landing, we had taking a lot of pictures. Landing on Mars is extremely challenging, and because we do not have the direct communication as the spacecraft is going to land, we do not have direct communication with our spacecraft, because it takes about 8 minutes, 11 minutes for the signal to come from Mars to Earth. So And then as it was going down, as I said, we do not also have the current information of the winds conditions on Mars. So it can actually drift and go somewhere else, as it is going down. So but we have to land at a certain location. Why? Because Mars has a lot of boulders, a lot of big stones and all. We don't want to land on one of those. So what we had done before, using our other resources like MRO, Mars Reconnaissance Orbiter, we took a lot of pictures of the place where we want to land, and it fed in a machine learned system, so that as the spacecraft is going down, it was always comparing what it's seeing with the database that we had, and then it adjusted its thrusters in a way to at the last moment to go and land at the right spot. So we are already using either your image processing, data processing, and machine learning techniques to use in that domain. That is one of the domains. Of course, there is vast area where you can use these new technologies to get things done better. But one thing I will just tell young professionals who are just coming out of college perhaps and starting their career, that you should be very careful about using these technologies. Don't use them randomly, in the sense, if you don't understand it, first thing, if you want to be a good designer, if you want to make a good impact, you'll have to understand the basics, that what you are doing. As we used to say for programming, when the computers came, programming started, people used to garbage in, garbage out, that we used to talk about, that if you don't understand. Same thing here as well, that we really need to understand the basic, that what exactly we are doing, what is our ultimate goal, and then trying to look at what is being produced by all these softwares, that does it really make sense, so that part is very important, and that you'll be able to understand whether something makes sense or not only when your basics knowledge are solid.
Understood. So I would like to, since my role is also into airline domain and safety management, I'm keen to understand how safety considerations are integrated into these space missions, and what kind of safety protocols NASA is having at the moment.
Yes, so I won't
Maybe.
be able to tell you all the safety protocols because I'm not an expert in that domain, but I can tell you that what we do, because of course safety plays a huge role in whatever we do, because you can see that one of the motto for NASA is failure is not an option. So because we cannot go and fix them, right? But even though we say that, but we know that failure is the pillar of success, that we know, and we fail. We fail in many ways. But one thing is that failure is not an option, means that we have to learn from our failure. That lessons learned for each and every mission is very important, very critical for the future success of NASA. So that is, for anything we call it that safety management and assurance. That is a complete a division there with NASA. For whenever there is a project, whenever there is a mission going on, every single component, every single system, every single subsystem has to have that safety part and mission assurance part built in, integrated to that. That not only the safety, when you talk about safety, there's multiple layers. You know more than I know. There's multiple layers to the safety part, that the components that you are using, that the safety of that, then people who are working under those circumstances, working on those projects, their safety, spacecraft safety or instrument safety, safety. So multiple ways they are connected. And then for any project for NASA, from the beginning, from your design phase itself, we involve the safety people, safety and mission assurance people, because that's how you cannot just do something and at the end say, okay, let's see what are the safety protocols, can we meet those. If you do that, it's too late. So you'll have to have that built in in from the beginning of your your project management. So that's what NASA does, and that's why we have been so successful.
Okay. And so with the safety, and with the space exploration domain, there's a significant risk as well. So, are there any practices NASA is having, like they can give as general practice to anyone when handling these high stakes missions?
Yes. Okay, so this is a very loaded question, a very critical and important question, because risk management is also extremely critical, because any big project when you are doing, you assess your risk, right? That could be so many different layers of risk, schedule risk, your cost risk. Like recently we had this big problem of getting all the components, right? That was globally. Uh, 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 so that slowed down after the pandemic. It slowed down the supply chain, and that impacted in a big way. So that played a huge risk. That was a big risk. So whenever we do even write a small proposal, trying to do a very low, what we call TRL, technology readiness level, that we are just trying to build a component, let's say. So that is very low TRL. So it is not really ready to fly, or even in that, when you are writing that, we have to assess the risk. That what is the risk and how can you mitigate that risk? So you cannot just do, when you are doing a risk mitigation, you cannot just put some money and say, this is how I'm going to mitigate risk, because everything is so intertwined that the schedule will be impacted if there is some risk element there. And then, so that's why many cases we have to think about redundancy, because if something is very highly critical, let's say communication link, we need to have communication right all the time. So do we need to have redundancies? Because if there is a risk of something failure, right? So but redundancy means money. So risk assessment and risk mitigation, all these are tied together. It's kind of a very critical optimization process, that how much risk you can tolerate without breaking the bank. That if you try to do any mitigation, that might cost a lot more money. You have a mitigation in idea, but it might cost too much of money. So then that is not going to work. So how do you then think about something else? So all these things that we really think from the very low level to all the way to the mission. So that is the practice that is needed. So we should all, now I'm learning, because I have this experience, that maybe as a student, we should also learn about risks for every decision that we make, and then what are the mitigation that we can do. So to think in those terms, it opens your eyes.
Yeah, so I know, like, we are running out of time. Also, I would have plenty of questions to ask from you. So what final advice you can give to the young scientists, engineers, or professionals like myself who aspire to work at institutions like NASA, and what kind of skills, mindsets we should develop, uh, and what kind of background actually, like, we should possess to get some opportunities like in global organizations like NASA?
Yes, so I always tell people, first of all, one of the most important thing that you should do, all of as a young students, young professional, you should all do. If I may say this, I don't call it an advice, but just saying that this is how you should think about is, you should pursue your passion. It is not about, you said, if I study this, I have a better opportunity to get to this place. I don't think, at least these big organizations, these very top high level organizations, we do not think in those terms. We want to find someone who is very passionate about whatever they do, because that part is critical. If you are pursuing your passion, you are a happy person, and your contribution will be much more than if you are in a job where you don't like, but you are just there, right? So my suggestion will be to find what your passion is. It's not easy. I know it is easier said than done. If you are studying undergraduate, you do not have all the knowledge of all these things that is happening around you, and you still don't know what exactly that clicks with you, that what exactly is your passion, but you still have a little bit of idea in you. You'll find that, I will give an example, that you'll find that sometimes someone will say that, oh, I don't like this particular subject. But you go to a class and there is a professor or teacher that is there and is an amazing teacher, and you love that, what you learned there. You see that, you realize you didn't even know that was a possibility, and something was there inside you that loved that particular area. So don't focus on that, okay, I study nowadays everyone wants to study machine learning, AI and all. But if you think about it, what is machine learning, what is AI, at the fundamental level, it is same those basics, right? So if you understand your physics well, if you understand your math well, you can be a great contributor in your AI machine learning area. Because you know how these things are coming together, what is the underlying principle behind them. So just find your passion, focus on this. And one thing I always say, that you'll have to work hard. There is no alternative to hard work, because if you might be very smart, but if you don't work hard, you are not going to achieve what you are trying to achieve. So that part is extremely critical, that you set your goal, but dreams remains just dream if you are not working for it.
Yeah.
I always tell people, dream big. Always dream big. I used to dream really big because it doesn't cost anything to dream. That is the one of the beauty of it. So dream big. However, you'll have to work to achieve that dream. You have to really, do hard work to achieve that dream. So find your passion and work hard. And you should be honest to yourself. I always say that you can, suppose you are trying something and you don't succeed, and someone will say, oh, you can go and tell them, oh, I tried my best. But you should look in the mirror and ask yourself, did you really give your best? Because you can never lie to yourself. So if you found that, yes, you have given your best and something didn't work out, it's fine. You should not be hard on yourself, because you gave your best. So then there are many other external factors that comes into play. So you should not blame yourself. So work hard, find your passion, and be honest to yourself. I think these are the three suggestions that I will give to all of you. And take failure or success in your stride. Do not allow your success to go to your head. And do not, same way, do not be too hard on yourself if you fail. If you fail, stand up, try to learn from it and move on.
Thank you. So thank you very much. It was so inspiring, and yeah, I also got a lot of things. And just one thing came to my head. Is it okay to get 1 minute? So
say it again.
Yeah. Yeah. Just 1 minute to give. Like something came to my mind. Like when you told about that, NASA is exploring how stars are forming, creating. So if they can find the way the stars are forming, they can create artificial stars or like that.
Yes. So that has been some dream of some scientists to actually do something like this. But the scale of energy, scale of mass, that all that is needed to do something like that in a lab is maybe in a small scale. I won't say it is impossible, but we are not there yet, because if you see we are understanding how it's formed, what kind of energy level are involved, for all this. So maybe
And
in
then,
future.
yeah, and then if they can create stars, then with high gravity, so that people in Earth will go to that stars. I mean, because due to the gravitational power.
So yes.
That's
Yes, so these are science, it's like sounds science fiction, but if you think about it, that is, you have to know what process goes on there, right? And then create something in the lab artificially, but you'll have to see what kind of energy level, what kind of, the lab stuff that you need to form that. So it is, beyond us at this point. But maybe you all will be able to come up with some solution that will be able to do it.
Yeah. Thank you. So you are in US. You are not.
No, I'm in the US right now. I'm in Pasadena, California. It's 8:40 a.m. on Sunday.
Morning. Okay.
Morning. Yes.
Okay. Thank you very much then. Thank you very much. So maybe in next, like, after a couple of months, I'll be able to catch you up again. Sorry.
Sure. And also,
yeah, we'll do that. Thank you very much.
Thank you. It was very nice talking to you, and I wish you all the best that you are pursuing.
So, thank you very much for joining this incredible video with me. If you feel this is valuable, and if you are an enthusiast in these domains I'm talking with the global leads, do subscribe, stay tuned, and like, watch, and share my video with your audience, your circles, so that they'll also get to know, and you can also share this knowledge. Thank you very much.